All right. So hi guys. There's more people joining. We're gonna get started. This is the exam 1 review session. So exam is tomorrow. A little scary. Don't forget that, just like some reminders, you can have a cheat sheet, I think like front and back. Preferably handwritten, but I don't think Laura had like a strict no typing policy or anything. Just kidding. I think she does. I'm sorry. I can't make it to classes during the day, so I don't know like what she says in class. But yeah, so cheat sheet, write what you want on it. You do get like the amino acid chart, and then you get like nuclear import export as well given to you. So like don't waste up space trying to put that on your cheat sheet. Yeah, and then we're gonna have like some question, and like we'll pause along the way too. But if you have questions along the way, just feel free to shout out, raise a hand. If you're on Zoom, like write in the chat or raise your hand too. All good.
Yeah, I'll keep the chat open.
Oh yeah. Okay, that works. Whenever you're ready.
All right, so we're going to start with some amino acids. We're going to go topic by topic, so we'll go 1 through 4. So that'll be the sequence of our session tonight.
Sorry.
Oh, no. All right, so let's go through the polypeptide anatomy. So remember that the N terminus is where the first, we're going to start the count, and then we'd go 1, 2, 3, 4. Remember, we're counting every alpha carbon, and not every carbon in the chain is an alpha carbon. And remember that R groups are arranged by chemistry and sterics. If you get a question on the exam, just like a problem set, you need to explain both. Yeah. So just some back, I'm sure we've gone through this 10 times, but the primary structure is a sequence of amino acids. They're formed by peptide bonds, which are really strong. So they have this double bond characteristic. Does anyone remember why they have a double bond characteristic? Yeah. Close. Yeah, that's true. That would affect sterics. Resonance, exactly. So this nitrogen right here can donate its to form a double bond between these two. This is 2 different amino acids. It can form a double bond. You don't need to know the chemistry behind it, but it's because of resonance. And yeah, that's why it's stronger. Secondary structure, remember, it's just the backbone atoms. There's no R group interactions here. It's hydrogen bonds between the oxygen on one and then another OH on the other, or an NH. And yeah, alpha helix R groups are on the outside, whereas in beta sheets, it goes up and down and up and down. Tertiary structure, this is where R groups start to matter. It's 3D folding. Yeah, there are a bunch of different types. You should know all of these different types and their strengths. So ionic at the top, London dispersion at the bottom. And yeah, the different type of interactions that can form, like a disulfide linkage and things like that.
And we'll get into like the specifics of each bond in a few slides.
Quaternary structure, very similar to tertiary structure, R group interactions, but this is between 2 polypeptides. So if you have one polypeptide and then another one, and they fold individually and then they come together, that's when you have quaternary structure. An individual protein can fold in different places into different shapes, but that is not quaternary. So here's the big difference. A tertiary structure is a single polypeptide, whereas a quaternary is multiple. It could be any more than 2. Again, they're stabilized by R group interactions, and we'll go through those type of interactions. And this is just like how they get there. All right, and so this is where the quaternary versus tertiary. If an individual polypeptide, just one long chain of amino acids, folds in one place and then folds in another place down the chain, those are domains. But once you introduce that second polypeptide, then it becomes subunits. Each one of those polypeptides is a subunit. So yeah, make sure you get that.
Sorry.
Oh, no, you're good.
Okay.
Where domains are part of tertiary structure, like you have one polypeptide.
Yeah.
And then it links both.
Mhm.
So subunits are specific to only quaternary structure?
Yeah,
Okay.
yeah.
But you could have domains within a quaternary
Within a-
structure. Yeah.
A subunit can have many domains, yeah. So, yeah.
Like a domain is like an alpha.
That would be more secondary structure. It would be more, did we go any really good examples in class? There are
No,
proteins that
it's
fold
hard
for
to-
one function outside of this. So you know, a cell membrane, one part of the protein might be out here and it'll fold in its own way. And then inside the cell membrane, it'll fold in a different way. And those are two domains. They don't necessarily have to be alpha helices.
Yeah. So like, for example, this is a domain, the blue area, but it has like alpha helices and beta sheets, but that's all one domain because like all of those amino acid groups are folding to each other and interacting with each other in that area. Whereas like all of these are interacting with each other in their own area. So that's what's causing like the domains. Does that make more sense? Okay. Any other questions on like amino
Structure,
acid
yeah.
structure, like this type of stuff? That's gonna be in
On the
a
R groups, yeah, we'll definitely do
slide.
that.
Yes. Okay. What is this? Okay. So going into specifics of R group interactions, bonds, amino acids and such. This is also in one of the slides, like we'll rank it as well so that you guys have a clear picture. But just going over the difference between polar and non-polar first. Polar is when you have an uneven sharing of electrons. So that's when partial charges come into play. Essentially, the difference in electrons and where they go is based on electronegativity. So if you're more familiar with like Gen Chem and like the periodic table, some elements are more electronegative than others. And so some examples would be like oxygen, fluorine, nitrogen, and sulfur. Those tend to be more electronegative. They're in like the top right corner of a periodic table. So that's where electronegativity, it means like they want to like hog the electrons more to themselves for simplistic sakes. That's why they would have like a partial negative charge. They don't keep it all the time, but they want it most of the time. And so for in this example of like water, you have the oxygen holding more of the electrons, so it gives it a partial negative charge, whereas that leaves the hydrogens being a little bit more positive because they don't have as many electrons around them as much, so they get partial positive charge. And then that's what creates like a dipole. You have like the partial positive or partial negative. On the other hand, you can have a non-polar structure. It's when your electrons are spread out a little bit more evenly. Typically, it is where they're like a little bit more symmetrical. So you're not going to have partial charges. This is when, rather than having like different electronegativities, you're going to have more similar electronegativities. So if you have like two carbons next to each other that are bonded to each other, they have the exact same electronegativity, so they're not going to be polar. Carbon and hydrogen have pretty similar electronegativities, so that's not going to be polar either. They're going to be pretty similar. So examples would be like if you had OO, CH, CC, HH, things like that. No difference in electronegativity or very little, so that you're not going to have like a difference in charges. Okay, so going into the types of R group interactions that Van was talking about a little earlier. So you can have polar charged R groups, which are the green and the purple box, polar uncharged, which is the blue box, and then non-polar R groups, which is the yellow box. So going through one by one, the charged R groups are typically going to make ionic bonds. Think of it like they are permanently charged. This is different from what we were talking about a second ago about like dipoles. These are permanently charged. They're always either permanently positive or permanently negative. And so those are ionic bonds. You can have polar uncharged groups down here where, again, this is where like the dipoles could potentially come in. So you might get partial charges. And for that reason, they're most likely going to be hydrogen bonds in the case of amino acids specifically, because most of them have hydrogens involved. They are hydrophilic, so they're water loving. for the sake, for like, if you want to explain like the chemistry, which typically on exams you do want to explain the chemistry. If you're interacting with water, water is like partial negative, partial positive. These polar uncharged groups also have like partial negative, partial positive areas. And so they can interact with each other, forming hydrogen bonds. And then that's why they're like a good fit for each other between water and the polar groups. And again, like the difference in electronegativity. Last group is the non-polar group that we talked about as well. They are hydrophobic. So sorry, that just threw me off. Okay. That is so true. Thank you for whoever requested that. Yeah, so the non-polar groups are no difference in electronegativity or very little. So there's not going to be dipoles. Mostly the way you can tell is CC or CHs. So sometimes Laura will like to throw out like an amino acid that just doesn't exist. And she'll be like, is this a polar or non-polar group? And then the way you can tell is that obviously you try to find it, it doesn't exist. So if you see that there's like a lot of carbons, a lot of hydrogens, you can argue that it's non-polar. If you see that there's like a ton of oxygens in it, you can argue that it's like, it's a polar group, things like that. But non-polar groups are usually hydrophobic. So those are weak interactions that typically are van der Waal interactions, sometimes called London dispersion forces. Okay, so polar charged R groups, again, this is kind of like a summary for those that might need to see it like different ways. Polar charged R groups can form ionic bonds with each other. An example would be like lysine and arginine, or electrostatic interactions or ion dipoles. That's another thing. You can have like a permanently charged polar group with a polar uncharged group. For example, lysine and serine, and then that can be an ion dipole bond. Or you can have just the polar uncharged together, and those make hydrogen bonds again. The hydrogen bonds for this case is only in the tertiary and quaternary structures. Hydrogen bonds do occur in the secondary structure that Van was talking about before, but that's not involved with R groups in the secondary structure. And then again, the van der Waal interactions and the non-polar R groups, just to explain a little bit more if you're unclear what they are, they're just like transient energy bonds that happen. Just like the electrons are moving around, there's not a lot of difference in electronegativity going on. So all the electrons are moving around, they're binding and bonding with each other momentarily, but they can like unbond and bond again very quickly. And then non-polar groups, they are hydrophobic. So that's where you get like the hydrophobic core or the hydrophobic clustering, where you'll find a lot of the non-polar amino acids in the center of a protein, trying to like hide away from the water around it. Okay, so disulfide bonds, these are ones that aren't talked about as often just because they don't happen as often, but are very important to know. These are the only covalent bond that you have to worry about and that occur for R group interactions. The only covalent bonds in this class, for the most part, are like these disulfide bonds and then the peptide bonds in your amino acid chain. But for disulfide bonds, they only occur between cysteine molecules, so you can only have them between two cysteines. And then because they are covalent bonds in this class are extremely strong, so they stabilize tertiary and quaternary structures very well. And yeah, they're the only covalent bond because all the other ones are not covalent. So just kind of like questions to go through. Are disulfide bridges found in all structure levels or just tertiary and quaternary? Yeah, just tertiary and quaternary, because they only exist in the R groups and you don't have R group interactions in any of the other structures. What about, based on your knowledge so far, what level structure is this image? Yeah. Just kidding. I thought I had a slide where it like showed the answer. It doesn't, but those are right. For the recording, it was just tertiary. Okay, and then this is just a bond summary for if you want to look it over, kind of like a review slide. If you want to put this on cheat sheet, go for it. Okay. Oh, yeah.
So are there also hydrogen bonds between R groups and the backbone? Do we need to know about that at all?
They can occur. It's just not I guess like it's not that it's not common, it's that I guess it's not very like focused on. So theoretically, like your R groups can interact with the backbone if it wanted to. But usually the way that she asks questions, it's like separated into like different structures, like secondary structure does this, tertiary structure does this. Yeah, but it can occur. How does a protein fold? This just shows kind of like a more visual explanation of a hydrophobic core where all of the non-polar amino acids are kind of hiding away from the outside. Okay. Any questions about bonding and R groups interactions?
Can I ask one more question?
Yeah, of course.
So there was a problem set question, I think problem set 3, and it was asking about tyrosine, which is labeled as non-polar on the amino acid charts, but it was saying that like tyrosine could hydrogen bond because of the OH on the end. So I was a little confused about that. Is it just that like because of the OH and because in all cases with the non-polar amino acids where they do have like an OH or an NH, they can still hydrogen bond? So
tyrosine is kind of like a special scenario. There are certain amino acids that are special, tyrosine being one of them. It's considered non-polar in some cases because of like the huge phenol ring. So it has like a lot of C's and H's, but because of like the big OH, or not the big OH, the OH at the end, that could make it also possible to like do hydrogen bonding. So a lot of it is kind of like context relative. If you were comparing like tyrosine with like a really polar amino acid, and it asked like which one would be more polar, you can go based off of that. Yeah, so it's just good to know that it can make hydrogen bonds. And then if it asks you a questions like that, to like cover your bases and be like, oh, this is also a possibility. Yeah. Mhm. All right.
Awesome. Let's do some protein modeling.
It's coming.
Who can list all 4 models of protein modeling right now?
Backbone, or well, that's wireframe, sorry.
Okay,
yeah.
Sorry.
No, great.
Ribbon.
Yep.
Almost space filling,
Yep.
and yeah, isn't backbone and bond stick are different, right?
Yeah.
Wireframe, yeah.
Yeah, you got it. Awesome. All right. Perfect. Do you want to explain what each one is?
Yeah, so ball and stick, it's kind of similar to backbone in the sense that it shows the peptide bond, but I'm pretty sure it also shows the R groups, right?
Yeah.
Just as balls. Backbone just shows the peptide bonds, like I said. Space fill, it kind of gives us, we kind of are able to see the size. I think it shows us tertiary and quaternary structure, I'm pretty sure.
Yeah.
And it kind of gives us just a broad sense of the size. And then the ribbon model shows us secondary structure with the alpha helices configuration.
And what about backbone? What does that show us?
And then backbone is just like the peptide bond.
Yeah. Fantastic. Beautiful job. Yeah, that's good.
Cool. Any questions on that? That was, yeah. I can't remember. Did it ever come up in the slides when you asked that question about like the order of strength? No. Okay. I thought it was in there. It might be later, but oh, do you want to write it?
but-
Okay. Oh, wait, I think I saw it. If you want this, there's like a tiny piece. Oh, yeah, that would work better. You got it.
Yeah.
Okay. While Van's
Can you
writing
see
that. Okay. While Van's writing that. Are you doing strongest to
Yeah.
weakest? Okay, so it's going to be strongest to weakest, strongest at the top. This is perfect.
This is horrible.
dipole induced dipole or we just do dipole
Uh, Just,
non-polar
yeah.
LPF?
yeah. They do have like iron dipole, but there's not, yeah. Okay. So weakest is like London dispersion / van der Waals. And then you have your hydrogen bonds, which is like the dipoles that we talked about with the polars. And then you have ionic bonds, which is like permanently positive and permanently negative together. And then strongest in this class would be covalent bonds. And then the only covalent